Hello students, so today in this lecture I will tell you the structural elucidation of citral. So citral is one of the terpenoid. So let's explain the structural elucidation of citral. Okay, so if we talk about the citral, then citral is one of the terpenoid. Citral is one of the terpenoid, and this component citral is found in lemon oil. This is one of the component of lemon oil and lemongrass oil. So it is found in lemongrass oil or lemongrass. It is found in lemongrass. So around 65 to 85% of citral that is found in lemongrass, and also it is found in lemon also, and there the percentage is around 5% citral is found in lemon. So this citral has a pleasant smell of lemon. It has pleasant smell of lemon, and so it is also found in, it is also used in a let's say perfumery industry also. And by using this citral, we can prepare other terpenoids also. So it is used to prepare other terpenoids. For example, it is used to prepare geraniol oil, it is used to prepare citronella and citronellol, it is used to prepare vitamin A, it is used to prepare one of the important perfumery compound, that is beta-ione. So this beta-ione, this is a very much used in perfumery industry. So this is used in perfumery industry. Okay. So another property of this citral, this citral is used as a antibiotic also, or antiviral agent. So it is used as antibacterial, antiviral, agent. Okay. So and antiseptic also it is used. So these are some of the important properties of the citral, found in lemongrass, found in lemon. It smells like a lemon, and that's why it is used in a perfumery industry, and it is used to prepare the other terpenoids, for example geraniol oil, citronella, citronellol, vitamin A, beta-ione, like this. Okay. So if we see this citral, the structure of citral, I am writing the structure of the citral. So if you see the structure of citral, it is something like this. This is the structure of citral. Okay, now I will explain the structural elucidation of this citral, or how we can determine the structure of this citral. So let's see the structural elucidation now. Or structural determination. So structural elucidation. So in structural elucidation, first of all, if we see the molecular formula, if we see the molecular formula of this citral, then by elemental analysis it can be determined by elemental analysis. Nowadays it can be determined by various other spectroscopic technique, but at that time when it was discovered, that is in 1896, around 1896 to 1898 it was discovered. Okay, so the molecular formula by using this elemental analysis, that was found to be C10H16O. So this was the molecular formula. Okay, now if we find the double bond equivalent in this molecular formula, so double bond equivalent DBE. So if we find double bond equivalent, then we know the formula for this double bond equivalent. So number of carbon atoms. So here the number of carbon atom is 10. Number of carbon atom minus number of monovalent atom divided by 2, means number of monovalent atom means hydrogen, divided by 2, plus number of trivalent atom divided by 2. So here there is no trivalent atom, no nitrogen is present over here, so that's why that is taken as 0. And for oxygen it doesn't, for oxygen we don't take anything in this dB, so plus 1. Okay, so formula for this is, formula for DBE, number of carbon atom plus, okay, number of or minus number of hydrogen atom divided by 2 plus number of nitrogen atom divided by 2 plus 1. So this is the general formula for DBE. This is the general formula for DBE. Now, so if we find this, then this is 8 and this is equal to 3. So DB is coming out to be 3. Here DB is coming out to be 3. 3 means either 3 double bond may be present, either 3 double bond may be present, or 3 rings may be present, or the combination of double bond and ring. So either double bond plus ring, that should be equal to 3. So this combination of double bond and ring, that should be equal to 3. So now let's find whether how many double bonds are present in this. So for this the another experiment that was done, that is we can do the hydrogenation. So hydrogenation by using the palladium catalyst, or hydrogenation in presence of bromine and CCl4. So the hydrogenation experiment was done, and if we do the hydrogenation of C10H16O in presence of H2PD, then it was found that the molecular formula that was determined after this hydrogenation, that was C10H20, and this is O, C10H20O, means 4 hydrogens are attached in this structure. So if 4 hydrogens are attached in this structure, then so as the name of this is Citral, so the name of this, that can be written as tetrahydrocitral. So I can write it tetrahydrocitral. Okay. Now in another experiment, if it is treated with bromine in CCl4, then what was found? So C10H16OBr4. So it is 4 hydrogens, 4 bromines are attached. 4 bromines, no doubt the 4 bromines can be attached over the 2 double bond. So that's why we can, it means the citral contains the 2 double bond, because 4 bromines are attached and 4 bromines can be attached over the 2 double bond. So suppose if 2 double bonds are there, then 4 bromines will be attached like this: bromine, there bromine, here bromine, here bromine. No doubt here some more groups may be there in between this, but 4 bromines are attached. So that's why what we can name it, tetrabromo citral. So what it proves? It proves the number of double bond. So it proves the number of double bond. So here the number of double bond, so this is equal to 2 according to this experiment. So therefore number of double bond, this is equal to 2. So this was the third experiment. Now next one, when now one of the oxygen is present in molecular formula, one of the oxygen is present. So that's why we can determine the nature of oxygen. So the oxygen may be due to hydroxyl group, it may be phenolic group, it may be carbonyl group, it may be aldehyde, it may be ketone, it may be acid. So we have to see the nature of this oxygen. So nature of oxygen, this is the next one, nature of oxygen. So to determine the nature of oxygen, some experiments were performed. So first of all, when this citral, when the C10 or C10H16O, this was treated with, when citral was treated with some hydrogen, suppose NH2G. Suppose it may be G, may be NH2 here, that is hydrazine. It may be phenyl hydrazine. It may be DNP also, dinitrophenyl hydrazine. So this may be also, we can use the DNP, dinitrophenyl hydrazine. Okay, so if this is treated with this hydrazine, then oxime was obtained. So if oxime, that is, and either the orange or yellow PPT was obtained when this was treated with hydrazine. So the formation of this oxime, it tells the presence of carbonyl group. That is, it shows the presence of carbonyl group. Now what type of this carbonyl is present? The carbonyl may be aldehyde, or it may be ketone, or some other. So whether this is aldehyde or ketone, okay, so that can be determined by the tolerance test or Felix test. So when this citral, was C10H16O, when it was treated with tolerance reagent, then what was found? The gyranic acid was found. Gyranic acid was found. Okay, so and when it was treated with sodium amalgam, then it was when geraniol is found. Geraniol was found. So the structure of this gyranic acid, that was determined. So it was and this is geranoil, the structure of geranoil. So this was So formation of this gyranic acid, formation of means oxidation of, here this oxidation of citral occurs, oxidation of citral to this gyranic acid. It means if gyranic acid is formed, means after oxidation if we are getting this acid, it means this citral, it should be aldehyde. So this shows that, and after reduction, so this is the reduction and this is the oxidation. So after this reduction we are getting the alcohol, and after oxidation we are getting the acid. So it means citral is aldehyde. So it shows citral is an aldehyde. Okay. Now another experiment was performed. So after this, next experiment that was performed is the nature of this aldehyde. So as in the structure, so if we see the structure, then this structure is alpha beta unsaturated aldehyde. So this is an alpha beta unsaturated aldehyde. So to prove that the citral is an alpha beta unsaturated aldehyde, it was treated with sodium bisulfite. So let's see after this another experiment. So now next experiment that was done is the presence of alpha beta unsaturated aldehyde group. So presence of alpha beta unsaturated aldehyde group. So for this the citral was treated with sodium bisulfite, and it was found that the citral consumes 2 molecules of sodium bisulfite, so it gives the bisulfite compound, disulfide compound. So citral disulfide was formed. Citral disulfide was formed. If we have this alpha beta unsaturated aldehyde, then if we see this molecule will react with 2 molecules of sodium bisulfite. This will react with 2 molecules of sodium bisulfite. One of the molecule will attach over this C double bond O, and another molecule, this is minus, this is plus, this would be minus and this would be plus. So this molecule, sodium bisulfite will, 2 molecules of sodium bisulfite will have 1 molecule over here, another molecule over here. So we will get the disulfide. Okay. So that's why, formation of citral disulfide, it tells about the presence of alpha beta unsaturated aldehyde group. Now next, whether this citral is acyclic one or cyclic one. So presence of cyclic, or we can say presence of ring, whether in citral ring is present or not, so that can be proved by converting the formula into the saturated hydrocarbon. So presence or absence of ring. So to prove this presence or absence of ring, that's what I told you, the citral formula was C10H16O. So as I told you, if it is converted into saturated hydrocarbon. So what I told you, there is two double bond and one carbonyl group. Okay. So if that is all this pi bond are converted into the parent alkane form or saturated hydrocarbon, then we should add here 6 hydrogen. Add here 6 hydrogen. 6 hydrogen. Why 6 hydrogen? 4 hydrogens from the double bond, carbon-carbon double bond, and two from the carbonyl, 2 from the aldehydic C double pi bond. Okay, aldehydic pi bond. So overall, if we can see, 3 pi bonds are present. So to make this structure saturated, we should add 6 hydrogen. So if we convert it into the parent alkane form, then this is C10H22, leaving this oxygen. Suppose if we leave this oxygen, so this formula, this C10H22, it corresponds to the general formula of CnH2n plus 2, and the presence of this CnH2n plus 2, it shows that it is acyclic in nature. It is acyclic. Okay, so we know that if we have this formula Cn, I am telling you CnH2n plus 2, then this is acyclic. If general formula is CnH2n, then it is monocyclic. And if general formula is CnH2n minus 2, then it is bicyclic. And if it is CnH2n minus 4, then it is tricyclic, and like this. Okay, so this is the way to determine whether this general formula corresponds to acyclic one, monocyclic one, bicyclic one, or tricyclic one. So this presence of so it means this is acyclic in nature. Citral is acyclic in nature. Now next experiment that was performed by the presence of parasimine skeleton. So presence or the skeleton, what type of skeleton it has. So presence of parasimine skeleton. So if the citral is treated with potassium hydrogen sulfate, then the scientist got the parasimine, this parasimine structure. So this is parasimine, and it means the citral has the parasimine type of skeleton. So parasimine type of skeleton means something, it has, the structure is something like this. The structure is something like this. Okay. So the structure is something like this, means one of the thing that it is monoterpenoid. So the structure is, so this is our tail, and this is head. So this parasimine, it has this citral, it shows this parasimine type of skeleton, and this skeleton, it is made up of 2 isoprene units which are joined in a head to tail fashion. So, and another thing, and that this parasimine, one of the methyl group is para to, or one of the isopropyl group is para to the methyl group, it means in citral also one of the isopropyl group is present, this is para to the methyl group. So the formation of this parasimine, it tells that there are two isoprene units which are joined in head to tail fashion, and second thing, the citral contains this one of the isopropyl group para to the methyl group. Okay, so what we can write, it means citral is a monoterpenoid having two isoprene unit joined in head to tail fashion, and contains one isopropyl group. Para to the methyl. Okay, so this experiment, it tells the presence of such skeleton. Now next experiment that was performed for the presence of or the position of double bond. So already what we have proved, two double bonds are present, and one aldehyde group is present. So now let's see what should be the position of this two double bond and what should be the position of aldehyde group. So now next experiment, position of double bond and aldehyde group. So this position of double bond and aldehyde group, that was proved by the oxidative degradation study. So by this oxidative degradation study, so first of all, this citral, if we have this citral structure, suppose I am drawing this citral structure, then first of all it was treated with alkaline KMnO4. When we treat it with alkaline KMnO4, then diol will be formed across the double bond. So let's form the diol across the double bond. So one OH group over here, another OH group over here, OH, this is another OH. Okay. Now it was treated with oxidation by this chromium oxide. Now these bonds will get broken now. Okay, so oxidative degradation will occur and these bonds will get broken, and what we will get? We will get here, so this part that will be converted into acetone. Suppose how we can see it, understand it. So we can join one of the OH over here, join one OH over here, another OH over here, so, and remove this H2O. Remove this H2O. In the same way, if we remove this H2O, then after removing this H2O, what we will get? We will get this acetone. Okay, we will get this acetone. Here in this case, we will get aldehyde. And aldehyde further oxidation, that would be converted into acid. In the same way, if we if we write one OH over here, after breaking another OH over here, again breaking, then again this H2O that would be removed, this H2 that would be removed, and here that would be converted into keto group. So plus what we are getting, so we will get this CO over here, and that would be converted into COOH. That is converted into COOH plus. So plus, now after removing this one, CHO that would be formed, and further this CHO black zone that would be converted into COOH. Okay, so this will be the degradation product. So now this is called as the levulinic acid. This is called as the levulinic acid. Okay, so these are the degradation product. So it means by seeing these degradation product, so it confirms the presence of double bond. It means if this is formed, it means one of the double bond is present over here, another double bond is present over here, so that we are getting this COH, and here we are getting the keto group. So keto group and this COH group is only obtained when one of the double bond is present over here and another double bond is present over here, and the CHO is present over here, so that we are getting this one. Okay, so this is the oxidative degradation study, so which proves the presence, the position of this double bond. So another final experiment that was done, that was the Verley's work. So let's see the Verley's work for confirmation of structure. For confirmation of structure. So Verley's, what this Verley's do? So he took this molecule, that is this, if we have the citral, then this was treated with aqueous. It was treated with aqueous potassium carbonate. It was treated with aqueous potassium carbonate. So what was found out? He got the product that was formed. So the product was methylhexanone plus acetaldehyde. Okay, so this was the product. So methylhexanone, and these product was formed. And these products are the retroaldol product. So these were the retroaldol. So these were the retroaldol products, or this reaction is the retroaldol reaction. Okay, so how can we see it? So this means using these two, methylhexanone and this acetaldehyde, again we can get the citral molecule. So in presence of base, it will form a nucleophile over here, and that will attack over here, this will go over here, and finally the removal of this H2O molecule will get. So this Verley's work further proves the structure of this citral. Now further this methylhexanone further, after this ozonolysis, this will break like this, and we get the product. So we will get here levulinic acid plus this acetone. So this is the structural elucidation of the citral. Now in next lecture I will tell you the synthesis. So finally the final structure was proved by its synthesis. So in next lecture I will tell you the synthesis of citral. Oh, thank you.